Hey there everybody, this is the lesson for the grade 10 MIAP students. This is chapter 5, lesson 3, interpreting and sketching graphs. So we're going to start with a quick refresher on what independent and dependent variables means. The independent variable is what we also call the input variable. And it is defined by the experimenter. It is also the x values on the horizontal axis. And this part here about defined by the experimenter very often confuses students because, for example, time is very often the independent variable. And it confuses students because they think, well, you can't control time. How does the experimenter set the time? But the experimenter chooses how often to record time. You record the time in the experiment, or you take a measurement in your experiment every 30 seconds or every minute. So those are the things that are controlled by the experimenter. The dependent variable, also known as the output or responding variable, is defined by the experiment itself. So this is the y values on the vertical axis. So let's make a quick sketch of that to make sure we all understand that the vertical is this way, right? So the y-axis is up and down that way, and this is my dependent along here. That's an E. And this is the x-axis, or the independent, along that way. Okay, let's do a few examples just to make sure we understand this concept. So determine which variable is the independent and which variable is the dependent in the following situations. So the relationship between the number of people at a party and the number of pizzas ordered. Well, the number of pizzas ordered, it would make sense to me, would depend on how many people showed up. Sometimes you can have an experiment where it really two variables both respond to each other kind of equally, and you could switch which one's dependent and independent. I'm almost tempted to say this is one of those situations if you wanted to make the argument that if you ordered more pizzas, more people would show up. But I think for the most part, the people would show up and then you'd order the pizza. So the number of pizzas ordered depends on the number of people at a party, I think would make the most sense. The cost in dollars of an MP3 player and the size of the storage space. This one's near and dear to my heart because I still use the biggest possible iPod Classic that I could buy. So this is where the size of the storage, actually now that I think about it, I think I'm going to say that the cost depends on size of storage. Right? The bigger the hard drive, the more it costs. In C, a survey was conducted to show the relationship between the number of years of post-secondary education and their annual income. So annual income, that means how much money people make, tends to depend, at least somewhat, on the number of years of post-secondary, which means number of years of education you have after high school. This, of course, would not be a direct linear correlation by any sense. There are people who didn't even finish high school who make a lot of money, and there are people who have PhDs who are unemployed. But for the most part, overall, the general trend would be this gets higher because that got higher. The number of kilometers and the age of a vehicle in years. Again, there would be exceptions. My mom has a vehicle that's now 20 years old and she hasn't even hit 100,000 kilometers on it. But that's an exception. For the most part, the age of the vehicle would determine how many kilometers are driven. And of course this one would make absolutely no sense the other way around, right? Obviously The fact that my mom doesn't drive her car very far doesn't make it go backwards in time and get younger. So how old is the independent, and how many kilometers get driven is the dependent. This depends on that. Okay, a couple more of these. Oh, ignore my scribbles there. See if I can focus that a little better. I think that's better. Okay, a city's, I think they meant Y''S. A city's average annual temperature and the geographical location of the city. And again, there are exceptions to this, but for the most part, for the overwhelming majority of cases here, I think you would definitely say that a sec here, that the annual temperature, annual average temperature, depends on how far north you are. Or even if it's not how far north, how close you are to a large body of water. When I was in the north of England, people of course hear that you're from Winnipeg, and they always wonder what it's like living so far north where it's so cold. And I do point out that while we are a lot colder in the winter than you are, we're actually not as far north. And they didn't believe me until they looked it up on Wikipedia, and sure enough, London is slightly further south than Winnipeg, but by the time you're in the north of England, you are further north than Winnipeg is, which blew their minds, because they always, as most people do, associate northwardness with coldness, which is true basically, but the fact that they're so close to an ocean, which is still geographical location, is what regulates their temperature so it's not so cold. The profit of a company and its sales. I think this one's pretty straightforward. Your profit depends on your sales. And the temperature of your food and the length of the time you have it in the microwave. Well, how long you have it in the microwave is your input. And again, the thing that you set as the experimenter, and the temperature of your food is the output. And so you're going to get graphs like this in this part of the chapter. And you're going to see that there's a lot of information that you can glean from a graph like this. Notice that from here to here on the graph, you have a steep increase and a very positive slope. Then you have a steep decrease and a very negative slope. And of course, you'd be heading back towards the direction you started from. This is a distance time graph. You remember these from science class likely. And then this flat part is where the distance doesn't change. You're not moving towards or away from your starting point. So you'd actually have a speed of 0. And then you'd have a very sort of a moderate increase and then a moderate decrease in distance. So again, now you might want to, you might be confused by these graphs. Remember how these work. Let's go back to the first two lines here. This is actually a faster speed than this one, but the difference is that going up and going down is, of course, which direction you're going, right? This is moving in a constant speed away from the starting point, and this is moving in a constant speed towards the starting point, and this one's faster because it's steeper. So keeping all these things in mind, remember, I'm throwing around the word slope. Remember, we've been kind of in our classes lately reviewing old grade 9 graphing skills, and this number here is the measure of slope or steepness of a line. And if m is a positive number, the graph has to have a line that's going upwards. And sorry, I'm off the screen. If m is negative, you would have a, we'd call that upwards, and we'd call this downwards. Downwards, sorry, that's a W. Downwards. And think of it as you read from left to right, so that's upwards. Because I know you could say, well, it's upwards if you go that way, but we read from left to right, so we interpret graphs from left to right as well. So that's a downward slope, that's an upward slope. So in an equation, this m here, this would be a positive number in front of the x, and this m here for that line would be a negative number in front of the x. Okay? So we'll do more review of grade 9 graphing in future classes. For right now, let's start interpreting some graphs. So let's take a look at this graph. Each point on this graph represents a different person. At which variable is the dependent variable and which one's the independent variable? So obviously, height depends on age. The oldest person on this graph is person G, and that person is 18 years old. The youngest person on this graph, why don't you pause the video and try to fill in the rest of these questions here, and then we'll go over them together. So take a second and pause the video and try them. Okay, did you try them? So which person's the youngest on the graph? The youngest person is A, who isn't even a year old yet. The two people with the same height are B and C, right here, because they are the same vertical height. And that height is 100 centimeters. And the two people with the same age are the two people who are horizontally the same distance, which is E and D. And they are both 10 years old. And now this is an interesting question. Which person, B or C, would you say is taller for his or her age? And you'd say that about B, because B is younger than C, but is the same height. So you'd say that person is tall for their age. Right? Okay. So, moving along, let's dig deeper into one of these graphs. This graph represents a day trip from Winnipeg to Portage la Prairie, a distance of approximately 140 kilometers. Describe the journey for each segment of the graph. So the first thing we got to do is we got to recall that S for speed, or those of you who remember this from physics, you could also call it V for velocity, is equal to distance divided by time. And think of the distance, of course, as being the rise, and the time as being the run, and rise over run is the same thing as saying slope. So let's break this down into all the segments of the graph. From point O to point A, so that's from time is 0 to time is equal to 2, the graph is going upwards. So as time increases, the distance from our starting point, which is Winnipeg, also increases. And let's describe the journey. I can describe it in lots of ways, but what I'll say is that we drive 140 kilometers in 2 hours, which means that we have a constant speed of 70 kilometers per hour. And by constant speed, what do I mean by constant speed? Well, I mean that this is a straight line from here to here. If this was a curve or a wiggly line, then that would mean we sped up and slowed down and sped up and slowed down. Our acceleration would be changing. But in this case, it's a straight line, so it's a constant speed. If this was a wavy line, and I still went, well, it's 140 kilometers in 2 hours, so the point from here to here, I would have called this an average speed. But this is a constant speed, not an average speed. Okay, from time is equal to 2 to time is equal to 3 will get me from points A to B. And this graph is horizontal. It actually has a slope of 0. So as time increases, distance from Winnipeg doesn't change. And I would say that we have stopped in Portage. Let's just say Portage instead of Portage la Prairie, if that's okay. Looks like we've stopped for 1 hour. So that's a slope of 0, so we have 0 speed, so we have stopped. The next chunk of the graph is from B to C, and that's from time is equal to 3 hours to time is equal to, I'm going to assume that that's half of half. If you look at this point here, looks like it's about, this would be 3.5, so that's half of the next one. So I'm going to say that's 3.75. You can go to minutes if you want, 3 hours and 45 minutes. The graph goes downward. So as time increases, the distance from Winnipeg decreases. And this would obviously be where we are driving back to Winnipeg. And we go 50 kilometers in 0.75 hours. And if you do the math on that, you get a constant speed. Again, it's a straight line. That's how I know it's constant. And you get a constant speed of 66. I'll round it to 1 decimal, 0.7 kilometers per hour. If you're wondering how I got this number, I went 50 divided by 3/4, which is 66.6 repeating. Okay, so from C to D, once again, we got another flat part. So from t is equal to 3.75 to t is equal to 4.5. That is another horizontal part of the graph. And as time increases, distance stays constant. And it looks to me like we stopped for 45 minutes. Got gas, got lunch, somewhere between the two cities. And then our last chunk from D to E is our actual biggest, our fastest speed, because it's the steepest line. And from D to E would be from the time of 4.5 to the time of 5.5 hours. And that graph goes again downward with a negative slope. The distance from Winnipeg is decreasing. And of course we hit 0 at point E, which means we're back in Winnipeg. And so this is drive the last 90 kilometers back to Winnipeg in 1 hour. So that would be a speed of 90 kilometers per hour. All right, so that's how we interpret graphs like that. Let's see if we could make one. So let's read it through together. At the beginning of a race, Alicia took 2 seconds to reach a speed of 8 meters per second. She ran at approximately 8 meters per second for 12 seconds, then slowed down to a stop in 2 seconds. Sketch a graph of speed as a function of time and label each section of your graph and explain what it represents. Okay, so I'll let you pause here and try drawing it for yourself. The difference between this one and the last one is that this graph is, of course, velocity and time, not distance and time, which means that all of its slopes, velocity divided by time, is called acceleration, if you'll remember that from your science class. So pause the video and try drawing the graph, and then we'll do it together in a minute. All right, how did you do? I'm going to start here. It makes sense to start at 0, 0. And she started from a stop, and it took her 2 seconds to reach 8 meters per second. So it took her 2 seconds to make it up 5, 6, 7, 8. And we'll assume that this is a constant acceleration. And then let's write that in words. From A to B, we'll call that A and we'll call that B. From A to B, Alicia accelerates. Oh, I'm off the screen, I'm sorry. Alicia accelerates from 0 meters per second to 8 meters per second in 2 seconds. And if you want to find the acceleration, then acceleration is equal to velocity divided by time, or speed divided by time. So in this case, that's going to be 8 divided by 2, which is 4 meters per second squared. And if you're wondering, if you ever didn't know from your grade 10 teacher that taught you science why acceleration is meters per second squared, well, you can kind of see it's velocity divided by time, which is meters per second divided by seconds. And when you divide fractions, you times by the reciprocal. So that's meters times 1, which is meters, seconds times seconds. So that's where you get that fraction of meters per second squared from. So if that was never explained to you mathematically, hopefully that makes sense to you now. Then for 12 seconds, she runs at approximately 8 meters per second. So it says approximately. So that means that maybe for 12 seconds, let's see, you know, she's trying to maintain a constant speed, but she's approximately at constant speed. She's slowing down and speeding up a little bit with every step. And for 12 seconds. So let's see, this is already 2 seconds. So we need to go to, or no, wait a minute. For how long does she run? For 12 seconds. She ran at approximately 8 meters per second for 12 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, there. My mistake. I overshot that line. So there. That's where she will hit that as part C. So from B to C, she runs at approximately 8 meters per second. If it had said she runs exactly at a constant speed of 8 meters per second, I'd have made that a perfectly straight line. Okay, and then for the last part, she slows down to a stop in 2 seconds. So that means we have to go to a point that's 16 here, and she goes right down to there. And I'll assume that she slowed down at a constant speed. So from C to D, we have a, I should maybe go back to BC here and say that, of course, she has 0 acceleration. And that's why the slope is equal to 0. And from C to D, you have a negative acceleration. Because she's slowing down from 8 meters per second down to 0 in 2 seconds. So you could again say that her acceleration is -4 meters per second. Oh, meters per second squared. Sorry, I'm off the screen again. There we go. And that's it. That's lesson 5.3.